I thought we'd talk about some areas that I think a number of you are more familiar with, going to sort of the single particle level of this area of physics, which I know is more contemporary and hopefully aligns up with what some of you are doing in research, whether it's quantum dots or whether it's defects in semiconductors. And think about, again, how we can play a little bit with this physics and maybe think about, might it be some type of technology, like this BBC image, which looks great but has no meaning at all. And again, I don't want to harp as like an ex-industrial guy, but I do think it's, some of these numbers, it's good to throw a few real numbers out. And these are numbers from Intel. 5 billion transistors produced every second, 24 hours a day on their fabs. It's just Intel. Okay, so that's a lot of transistors. 20 million transistors per person on the planet every year. So that's a lot of technology being churned out of silicon. Nobody can argue that isn't a large number. And so, I think it behooves us to think about a little bit if we can somehow harness this to do something very different. And if we can't, we can't. But it's an important number. And so what I thought we would walk through are some developments I think some of you are familiar with, and then merge into or morph into some areas that I think are a little bit new. Taking advantage of the fact that going from those experiments I showed you from like 5 to 10 years ago to more recent work where you have quite exquisite control of a single particle now in solid-state materials at and well above room temperature, what are the sort of interesting things you might be able to do with it? What are some unique ways of controlling it? And we're talking a little bit about theory and about how theory tools can play a role in helping us predict some interesting pathways for this physics through new materials and new opportunities for quantum state control, from imaging and sensing to storage, just different things beyond information processing. And I really don't want to talk for the next 40 minutes myself. So maybe you could say whatever pops into your head while we're taking this diatribe. A personal anecdote, a story about your advisor, anything. But don't let me just go through this. So just one slide of history again, because I do think it's instructive. These were a part of these early sets of experiments that were some of these accidental discoveries, and these were in commercial wafers of gallium arsenide. This is a nice example. These were just bought online as 4-inch wafers of gallium arsenide as substrates used for some high electron mobility transistors at the time. Were just substrates with different intrinsic doping of electrons. And these were these time-resolved Faraday rotation experiments. And what was interesting about these measurements is that you can see the spin coherence time changes quite a lot with electron doping density. It's the only difference in these measurements. A low temperature in a few Tesla magnetic field. But they were quite interesting because the charge lifetimes didn't change at all. Maybe 5% between all these samples. But the spin lifetimes changed orders of magnitude just by changing the electron doping. So when it was semi-insulating, you would generate electron-hole pairs, which would recombine, and the spin lifetime would be pretty short. When the material was metallic, the lifetime would be short. But in between, it got pretty long. And at this density, where the spin lifetimes were quite long, it turned out it was right at the metal-insulator transition in a semiconductor. So what was so special about the metal-insulator transition in a solid that would allow you to create quite robust coherence? Well, so this work was published in Nature after a lot of sort of discussion with the referees. And part of that discussion was, well, is this like donor electrons in silicon, where people had seen a long lifetime? And then the reason it was different is if you put a couple of electrical gates on top of this wafer of gallium arsenide and put a few volts, you could drag this puddle of a few billion electron spins, tens of microns through the material. This wave of coherent spins could just be literally pulled through the substrate, right? With some dephasing, but it was still pretty good. And this really captured people's attention because this length scale, you can see the 50 micron bar. So you're talking about 100 microns of pulling a puddle of coherent spins through a commercial wafer where nothing at all is done to this. Zero, no processing, nothing, out of the box. And at the time, the length scale or the feature scale of technology was about a micron. So we're talking about this distance. And suddenly, this captured a lot of attention in both physics and materials, because here you have a material that was already used for prototype technology. You know, gallium arsenide was always referred to as the technology of the future. It's still the technology of the future, largely. We have to edit that, by the way. But anyway, very, very interesting scientific observation. So this is the data I showed you before. Again, going to higher band gaps, that low temperature data would work at room temperature. And then, just in this last slide, before we go on to the other work, Mike and Mickelson and some others, I mean, her work showed that you could use pulses of light to take these populations and spin and do operations on them through the Stark effect on the scale of the laser pulse. So in 150 femtoseconds, you could manipulate through the Stark effect these coherent spins, rotate them different angles, back and forth, many, many times until these electron spins would decohere.
Can I ask you something? So Stark effect meaning that the electric field of the pulse was equal? Exactly right. So the pulse of light would generate an electric field that would shift the energy level very quickly, just for the time the light is on, so that 150 femtoseconds. So if you're an electron, and you suddenly see this energy level move, you think it's a magnetic field. You think it's the Zeeman effect. You just see the level move. So it was like, and in fact, to get these stabilized effects with a conventional magnet, you'd have to apply roughly 100 Tesla in that same time frame. But you could just do it with a little laser pulse using the Stark effect. And so she did these quite beautiful experiments showing this, and then it made people realize you could do tens of thousands of operations, you know, all optically. On these quantum states. Admittedly, there were low temperatures and high fields, but the fact is there was no physical barrier for this. And we talked about electrical generation too. So a lot of things were happening. And then, you know, in around the 2010-ish time frame, we're getting a little bit more recent, people began to try and squash all these billions of electrons to one, right? Think about whether or not you could use individual states as quantum bits. Now I think a lot of you are registering with this from your own work. And I would say a large part of the initial work was using 2D electron gases. Everybody here familiar with 2D electron gases? So 2D electron gas, sorry?
Yeah, something, so I need to picture sort of a blob of spins processing coherently, right?
Correct.
But it's not necessarily quantum or anything. Like, is it like classical magnetism, which is sort of coherent, or is there some quantum coherent?
So I would say it depends what sort of picture you're interested in. So each spin is a quantum mechanical two-level system, and there's an ensemble of them that are not interacting, by and large. So I think it depends how closely you're looking and what you're looking for. So you can describe all of that semi-classically, like you said, as a processing system that eventually dephases. Or you can think about it as a series of quantum mechanical systems, two-level systems beating at their eigenfrequency from that spatial separation in energy. But you're quite right. You know, what's been motivating work to get down to the single spin level is that's a very clean quantum mechanical structure you can define. So I don't know how to answer your question because it's a tough one. You know, if you end up with 10 single spins, is that quantum mechanical or classical? If it's 100, is it quantum mechanical or classical? Is it 1,000? And so what defines that? And I would say it's the interaction length and the context, because each system itself is a quantum mechanical structure. But it's a good question, and I think it depends how you're applying it. But people did definitely want one. And so a two-dimensional electron gas is simply taking two different layers of a semiconductor, right, where the interface electronic states can be created in such a way that you end up with a high mobility of electrons in the sheet. It's literally a gas of electrons. By putting some electrical gates, you can confine them through electric potential to a small region. As you apply a voltage, you can literally pinch this gas into a very smaller number of electrons to the level of just one. And that's what these experiments were. Quantum dots, individual electrons made by carving out regions of electron gas with potentials, right? Just squeezing the potentials into a one-dimensional and then zero-dimensional system. And typically the radius was about 50 nanometers for the confined electron. In these gallium arsenide materials, there were lots of nuclear spins, maybe 100,000 nuclear spins, and you had to operate at low temperature. But that was fine. The experiments were quite beautiful, and they worked very well. And some of the initial experiments were the ones done in Delft, with work at the University of Tokyo and Harvard. In this consortium, they were doing lots of beautiful 2D gas experiments. Then there were experiments of donor impurities in silicon. I don't know if any of you have been reading about this or following this work where phosphor dopants in silicon, right? Some of Charlie Kane's original proposals, right, had these beautiful ideas which then were realized. The qubit radius shrunk because they were donors to just a couple of nanometers, raised the operation temperature then, right, to a few Kelvin. Definitely more tractable. Spectacularly beautiful measurements on single particles. And then there's an interesting history of the Nitrogen-vacancy center at Diamond. There was early work at the Naval Research Labs in the United States where people were doing lots of ESR measurements in nitrogen-vacancy centers in Diamond for reasons to use them as sensors at the time. Tom Kennedy and others had big groups. They actually grew Diamond there. They implanted it there. If you really dig in the literature, you'll see there's quite an interesting history of this. And they found at the time that if you pulled out a carbon atom from Diamond and there was a dopant nearby, such as nitrogen, it would form an interesting type of molecular state with a bound electron that could be addressed at room temperature through a beautiful selection rule. Now, the electron wave function here is very tight, just a couple of angstroms. So if you look at this change from 50 nanometers to 2 to a couple of angstroms, suddenly you see that you can bring this to room temperature. So what was interesting here is a material system that was readily available, which is part of the beauty of this area of physics. Pretty much anybody can get these samples. And that's very important for pushing a field of science. If there are 3 groups in the world that can make the material, that's exciting, but not so helpful if you're one of us. For fields to move very quickly, you'd like a lot of people having access to things. So one of the nice things about this is a lot of people have access. And so I want to talk a little bit about this as one interesting system to push spintronics to the single spin level, and then how it's moving into other areas now through theoretical guidance. So I know some of you are familiar with this. How many of you are familiar with the MV centers in Diamond? Okay. So I'm not going to talk to you at all. And I'm going to go through this just very qualitatively to get a sense about why this is so tractable. This electronic state in a defect, and for a lot of us it's ironic. After so much work for so many years to make beautiful single crystal materials, oddly enough for spintronics, one of the most attractive systems to get the single spins is one with defects, where you actually want missing atoms. You don't want clean materials. I mean, sort of clean, but you want them damaged. And in a way that might have explained a lot of the past work in this earlier data I showed you, where I was mentioning in these materials where we saw lots of nice spin coherence, when we grew beautiful high mobility electronic structures, we never saw anything. But as we began to drop the mobility, because of defects typically in a material, it became much more robust to have coherence. And now we believe there's a link, that these defects in the past might have actually been critical for the same reason that individual defects are states of trapping and controlling single spin coherence. And I don't think it's a coincidence. One of the reasons that nature has been very nice about systems like this is that normally in magnetism, in magnetism, the way you lift the degeneracy of a spin system, right, is to apply a magnetic field to the Zeeman effect, right? You separate spin up and spin down. In a lot of semiconductors like this one, there's a crystal field, right? And the crystal field actually can lift this degeneracy through strain. And so from a spintronics perspective, one of the nice things about these systems is you don't need a magnet to lift the degeneracy. The lattice does this for you with strain, which is pretty neat. So now you can address a single spin system without a magnet and go to a single particle and do it at room temperature. And the magnitude of this crystal field splitting, which is this D term in the Hamiltonian, is around 2.8 gigahertz. So 2.8 gigahertz is a very convenient frequency. It's a microwave frequency. It's disturbingly close to a cell phone frequency. And if you've worked with these systems in the lab, probably know that or maybe you don't, that your cell phone can annoyingly affect these experiments quite a bit. If you've been looking for unexpected signals you've been seeing, it's likely to be your iPhone 6. If you do want to apply a magnetic field and tune these frequencies a bit, these spins have a G factor of 2, so you can actually tune these levels a few megahertz per Gauss. So a refrigerator magnet is plenty for doing this. And again, this makes a very powerful system experimentally, because those measurements I showed you earlier, you go to several Tesla magnetic fields, you need cryogenic systems. Now we're talking about refrigerator magnets at room temperature. Things are becoming much more tractable. And while there's electron spin here, this dopant nitrogen also has a nuclear spin, which at some level is sort of an annoyance, because spin-spin interactions, you imagine, will decohere a structure. On the other hand, if you take an optimistic view, nuclear spins have a very long lifetime. And you can think about that also as a local memory. If you can controllably move information from that one electron to that nuclear spin and control the interaction, every place you have an electron, you also have a local memory. So it's a very rich system just for making a defect in a lattice. It happens to be diamond, which historically has made things pretty expensive. And not that I always want to go back to industrial labs, but most of the major industrial labs in the world have had diamond programs at one time or another. So the United States General Electric in the US has had the oldest diamond program historically. It was a huge diamond program. Bell Labs did, Xerox did, HP did, IBM did. Why were they all interested in diamond? I should say for like 30 years. People working at diamond should know this. Not that you should feel any pressure, but
That was high power electron.
it's exactly right. I mean, besides quantum information, which a lot of us are very interested in, what is another property of diamond? It's arguably the best thermal conductor on the planet. And so the entire electronics industry, for as long as I can remember, have been trying to make diamond as a substrate. Right, to get that heat out of your Pentium chip, you'd love to grow it on diamond. And I cannot tell you how many people, when you look at these labs, how many large groups have been working on growing diamond. They've been trying to grow diamond on everything. And obviously it didn't work so well. We have a big diamond technology, but there's been a very, very, very long history of diamond. It's not just this field now that we work in. And the ironic thing is you can grow diamond pretty well on diamond, but it's the chicken and egg problem. You want the diamond to grow the diamond, but you need the diamond to grow the diamond. So you can try and make seeds and grow diamond crystals, right, which you can polish and cleave, but that limits your substrate size. What you'd like is a 3 or 4 inch substrate of diamond to grow things. Or so if any, by the way, are looking for a new thesis topic, let me assure you, if any of you come up with a scheme to grow diamond on something, say silicon, you should do 2 things. One, you should patent it. Then you can publish it. And you'll do really, really, really well. A lot of people would like this. But that being said, there have been a lot of studies of diamond. So the Naval Research Group I was telling you about, that's one of the reasons they were very interested in looking at the electronic structure of diamond, trying to understand what the crystal lattice information was, how it was growing, what the structure of the material was, what was the source of the defects, to try to understand how they could also grow it on different substrates. Okay. So one of the reasons that this is interesting for quantum information, and it's late, and we're not going to go through this in great detail, it's 9:30 at night, some of us are jet lagged, but nature has been very, very friendly about this, and it's created a very nice system that looks very much like a trapped atom, according to this done atomic physics. You essentially have a cycling transition, where taking unpolarized light will excite a structure from its ground state into an excited state, relax through a series of singlets, I see some disturbing laughter, into the ground state. And essentially, at the end of the day, it means by simply illuminating this material with an unpolarized light, you end up with a polarized electron spin, which is pretty remarkable. And you're doing all that within a 5.5 eV band gap. So now we're talking about an even larger band gap than the materials we were talking about before, so it's going to be very robust at and well above room temperature. And because of this crystal field splitting I was telling you before, this 2.8 gigahertz, it means that you can manipulate the spin, because you've lifted this degeneracy, with microwaves, which, if you're not trying to do anything incredibly fancy, is over-the-counter electronics. If you're trying to do very clever and careful, precise pulse systems, then it's very expensive. But to just manipulate these spins, you can do it just fine with a wire. So you can use light to initialize these spins. The spins luminesce from these states. You can read them out optically, but you can manipulate them electrically. And that's a defect-based semiconductor system. And what can you do with it? This is some data from about a decade ago, and I like this to show this because this was purchased online from Sumitomo Electric in Japan. It's just a commercial diamond sample. It's a few $100s. is a 20 by 20 micron scan of just taking a microscope objective after you've illuminated the system with light, during illumination, which is shown here in this green beam, through a microscope objective. You can move the objective around the sample underneath the objective, look at the luminescence that comes out, put it between a pair of through a beam splitter, through a pair of single photon counters, and just look at what comes out. If you look at the intensity, you'll see these spots, which are the defects. If you look carefully, you'll see some dimmer spots under the focal plane, because it's a three-dimensional sample. So this is just imaging in the plane. And if you park your microscope objective on top of one of them and do this type of experiment, look at the photons that come out, you can do a correlation measurement, an anti-bunching measurement, and convince yourself that it's the source of single photons. Right, so one electron, single photons. To convince yourself it's a spin, you can just put a wire nearby and put this 2.8 gigahertz radiation in it, and look at the change in the luminescence that happens as you hit that resonance frequency. That is the energy difference between the spin up and spin down state. And you see this change in the intensity. So it looks a little bit like electron spin resonance, but on one electron. And I can tell you it's this type of data that changed this area of spintronics. And it was these curves that had a huge impact in this field, because this was a lot of groups in the world have been coming up with very clever experiments at low temperature to measure a single electron spin. Right, so groups like the Dan Ruger's group doing these beautiful MEMS measurements to look at mechanical deflection of single spin states that worked quite nicely. These were really tough experiments that did address single spins nicely. But now being able to do this on a desktop, in the course of half an hour, on a single spin with zero field at room temperature, got people thinking a lot that maybe it wasn't crazy to think about using single spins, not just for some interesting physics, but maybe for applications. It's ironic, really, that putting in defects would let you do these measurements after so many years of trying to do single spin studies through some really tour de force experiments. If you read any of these Dan Ruger papers on the cantilever studies of single spins, these series of Nature papers, they're just astonishing. And people have used those techniques and harnessed them. Those of you that are doing optomechanics know that a lot of these processing techniques on the membranes and silicon nitride membranes were developed through that project. So, okay, not so hard to look at single spins. How fast can you manipulate a spin? So this was a project in my own group that was, again, driven a little bit through both a physics and a technology curiosity. So, people are pushing the limits of transistors to see how fast they can go, how many gigahertz will your chip operate. Now you can have a single spin system, and it's an interesting experiment to see how fast you control one spin. So there's an experiment that was put together with microwave connectors. Now this is a little primitive. Some coplanar waveguides. You can see some wire bonds. There's a titanium, platinum, gold shunt terminated waveguide here. It's blown up here. This is just titanium, platinum, gold wire on diamond deposited. Nothing super fancy, but oddly enough, every type of rare metal on diamond. So, it's the most expensive jewelry, really. There are defects in this diamond, which is here underneath it. You can see all the defects here glowing. We take one of them. Here's the metal around it. And we're going to just try and go faster and faster with radiation, microwave frequencies. How fast can you take one spin and do operations on it? This was some work that Greg Fuchs did, who's now has his own group up at Cornell. And it turned out, that there were some experimental issues, but like heating, but going up to a gigahertz was fine. And this is just an example of the time. This is from 2009, a few hundred megahertz Rabi oscillations, but on one particle at room temperature. And this also got a lot of industrial interest, because even now, if you look at your laptop and you look at what an SD RAM time is, in a laptop, it's about 5 nanoseconds. So now, on that same time scale of a few nanoseconds, you're taking not what we talked about with today's transistors, to maybe 10,000 electron charges on a gate, but one spin, right, and moving it pi in roughly nanoseconds, same time scales. So that's quite interesting. After a long time of pushing nanoelectronics, how many single electron charge transistors are on the market?
0.
Yeah, none, for the reason we talked about earlier. There are some lab demonstrations, but it's very, very, very hard to build a reliable structure that can manipulate or shuttle one charge.
But if it's the same time scale, is it better in any way?
Oh, this? I think it's largely useless. For anything practical. But, it's a metric to show that with standard electronics, you can take a single quantum object and perform an operation time on it, perform an operation on the same time scale as a classical charge technology, also using electrical gates. So I'm not saying this will lead to a spin transistor, but it just shows as another state variable, right, that you can manipulate at the level of a single electron now between two different states, and that's all. And that led to some experiments. That's one electron, and a lot of those early experiments were done using natural defects in diamond. But if you want to build something with it, you need to produce your own defects in diamond. And one of the things that we did was follow the same path that industry has done. It wasn't a new idea. The way that in today's technology that you want to place dopants in materials for devices is to use an aperture implanting technique that's done for transistors and other systems. You essentially make a mask with a bunch of holes, and you shoot ions through the holes. It's actually a very sophisticated effort. It's not just shooting ions through a hole, because if you shoot ions through holes, what sort of distribution do you get? Poisson distribution? Yeah. So, and so that's okay if you're putting 10,000 electrons, right, or 10,000 charges into a device. If you want one, you can't do that. So this is a hard problem, right? You can make the holes very small. You can do the ions. What's been very helpful in these techniques is to use standard codes that industries use, SRAM calculations, because you have electrons that scatter. You want to look at their penetration into a lattice. Industrial researchers realized many years ago that you can actually orient the lattice and actually have coherent scattering through the angles of the lattice to actually lower the energy but increase the penetration distance of the ion by using coherent reflections through the lattice. This has been modeled very nicely through a series of calculations. There's actually free online software called SRAM calculations and SRAM techniques. Still a problem getting this to the level of single spins completely reliably. But there are nice steps. Yeah?
Can you just spend minutes about this effect?
Yeah. So let's say you want to you want to damage something. Imagine as a graduate student, you want to damage something. Work with me on this. So, you shoot an ion into a perfect crystal, and you want to knock out atoms, right? Say down the path. You want to create defects in the ion that's lodged at some place. You've got some damage in its tail, right? And you want to somehow prepare the system after that so there's just, say, one vacancy and that ion is, say, nearby. Let's say you're shooting nitrogen in, and you want to create a nitrogen-vacancy pair. How do you do that? So ideally what you'd like to do is shoot the ion in to a very small distance. Then you'll heat the lattice to allow the defect to diffuse, right, through the solid, come into contact with the ion that made the damage and form a nitrogen-vacancy pair, and do that reliably. That's very hard statistically to make that work every time you shoot through, just because of these either Poisson distributions. It's a tough problem, and it's a problem that technology has been working on for a long time for electrical doping. That for different reasons they would like to put these ions in a gate, create damage or dopants in a certain place where the transistor gate is, right, and not diffuse. It's a source of leakage in transistors. So there's been a lot of effort to both simulate this and to do this. But to do this at the level of one ion is something that has not been worried about too much, right, for mass production, but now we're worrying about this. And so there are a lot of ways to think about doing it, and there are a lot of tricks people have used. But at the end of the day, one of the cool things about making this work is you have a remarkable length scale to play with. That's sort of a quantum engineer, right? Because you could build a technology at the level of a single electron to the hundreds of microns, all on the same chipset. So in terms of a playground for building things, it's quite remarkable. You could think about wiring quantum states together, using plasmonics to couple systems together over length scales that are quite unique. There are not very many examples of a technology where you can start from an individual electron to macroscopic scales all on one level of lithography. So there's a lot of fun if you can get these tools going, yeah.
So people working on donuts in silicon have basically the same problem.
Right, so like the beautiful work that Michelle Simmons has been doing, right, in Australia with the STM, right, to be able to manipulate and place single dopants in silicon. That has now been working. I think it's fair to say that's not particularly scalable. But yeah, that's been a huge development in this area. So for the idea of using phosphor dopants, that cartoon I showed earlier, part of the plan there that she and her colleagues would like to do in New South Wales is be able to put the dopants precisely where they want under a specific gate, or put them in certain places and then build the gates around them. And that's going very, very well. But yeah. So we'd like to see if we can do that with defects, because we'd like to do all this at room temperature and above room temperature. But yeah. So you can make pictures like this that look great, but in practice they have problems because some of these glowing regions are 1 spin, sometimes they're 2, sometimes they're 3, sometimes they're not glowing at all. So you can say, okay, how do people deal with this today in the real world with transistors? Well, they make a lot of transistors, and you probably know when you buy your transistor chips, a number of them don't work. Right, so there's a lot of built-in redundancy into the design because a lot of them don't work, and also they're burning out all the time as you use your PC. We know that, right? It's actually happening right now with that PC. But it's okay, right? There's enough redundancy built in, it's okay. There's a predicted lifetime, and it's going to be all right. So anyway, this is a very interesting direction, and a lot of groups are working on this right now, and it is a challenge. So one nice thing that's happened recently is by going to heavier ions like carbon and doing this type of implanting, you can damage very close to the surface. It's much easier to anneal, and you can increase the efficiency of this process in order of magnitude. So now you can get to like the 10% efficiency of creating these defects. Still not good enough for a lot of things, but from the student perspective, it's much better and cheaper and can be done overnight. Yeah.
For like quantum computation, this would be maybe a future system, right? But then you would do a quantum algorithm. Is there any way you can also manipulate all these little qubits in some like controlled way that you can do your unitary time calculation?
Yeah, so that's in a way the ultimate question, right? I mean, can you configure these in a way to do something powerful versus just making individual states? So my own view is yes, and so there are a couple of different approaches. One is people are building these in cavities and letting the photons do the interaction for you, right? And the advantage of that, of course, is that you don't have to precisely place them in a specific location. They sit within the modal volume of the cavity, and you have strong coupling in the cavity, few ifs there, but let's say that's happening. Then as long as they're in there somewhere, you can control the interaction optically. If you want to try an electronic version of this, and you can think about using like field gradients and other techniques to address individual states. If you have a gradient here, then they'll all have their unique frequency. And people have done things like that in other systems. Then it's a little trickier because you need to initialize the system with single spins that have reasonably well-defined separation. So not only do you have to create single spins, but you like their orientation to be the same. So you need to be able to prepare the system so that the damage creates states whose isotropy is roughly the same, ideally exactly the same. If you can do that, then I think you can control the individual states. I mean, to our own mind, for example, we think the photonic approach is a nice one because it gives you a lot of flexibility.
The photonic approach, you put the whole system in a cavity? Or?
So you can imagine, for example, one thing we've been doing is using photonic band gap structures with a relatively small modal volume, and you create the spins in the mode of the cavity. And that's been done. It works. It enhances the emission. It's not at the strong coupling level yet, at least in our own work. I'm guessing somebody will be doing this soon because it's literally a materials processing issue, like it is in every photonic cavity structure that's been built. If the processing is very clean, the cavities will work. So for photonic band gap structures, I know many of you work with this, you can do the calculation, get strong coupling and a certain Q. You build the system, you usually get the Q at least 1 or 2 orders of magnitude less than you would calculate. And then you could try and simulate why it's so low. And in most materials, not all, but in most of them, it's the fact that when you make a photonic cavity, the holes have to be very precise. If you have a very small change in the aspect ratio of this hole, meaning a few percent, the Q's plummet. And you can actually do that calculation quite accurately now and show that unless you really build these things properly, the Q's aren't going to work. If you build them right, though, they should be fine. That's been true in silicon. It's been true in other 3-5 materials. I'm sure it'll be true in diamond. They all have followed the same history of building pretty low Q cavities that did not have strong coupling. Almost all of them got the strong coupling. And I'm sure this will happen here too. And then it'll be very fun because then you also have built-in emission. So you have a nice way to read the system, prepare the system, and control the system. So just briefly, I wanted to mention that a number of groups have been able to move information from the electron into the adjacent nuclear spin. Largely driven by different materials, but all largely with the same idea, to take advantage of an anti-crossing between the Zeeman splitting of the electron spin and the nuclear spin in a region where the two are hybridized. And part of the motivation is that the nuclear spins can have long lifetimes. Nuclear spins traditionally do, mostly because they don't interact very much with the outside world. So if you can get information into them and come back later and retrieve it, you can do some nice work. And there was some initial work done both by our own group and by Misha Lukin's group at Harvard, using different types of materials and some different methods, so you could actually show that the concept does work. In our case, we showed the physics worked well, that it was fast. In their case, it did some beautiful measurement with some different material systems to increase the nuclear storage time to seconds. And the concept was, again, to take advantage of the fact that there's always a hyperfine interaction, right? So the nice thing about the electron and the nuclear spin is, again, nature sort of has given you the tools for it. You need a way to connect the electron to nuclear spin, and in physics we know it's a hyperfine interaction. So to make this work as a memory or some sort of device, you need to control when that interaction takes place and how fast it takes place. And then you can make a memory, in principle. So what Greg Fuchs did at the time is that he built a very fast series of coils to show that if you tune the system in this hybridized region where the electron and nuclear spins can interact. Landau and Zehner had a nice theory in the 1930s, quite some time ago, that has actually already been shown to work very nicely in atomic systems. This has all been done in atomic systems. But they showed that, in fact, in this hybridized region, the spin is both electrical and nuclear based on how long the system stays in this region of phase space. And based on how long it's there, the spin can be in the nuclei, it can be in the electron, based on the time. It's a hybridized state. So, and the probability of being in the state goes inversely with the rate of change in the magnetic field where you do this control of the interaction. That's actually what you'd like. So the faster you do this, the more likely you'll do the swap. And just to get to the end of the story, in these early experiments, the electron lifetime was this region in yellow, and this is the nuclear spin after you move the information in. And it's not a very good memory. It's not particularly useful for anything. But still, the storage fidelity wasn't so bad for a first shot, and these gates operated in about 120 nanoseconds, so they were pretty quick. And it was a one-atom nuclear memory. So there's been a lot of work to improve this. This storage time of 100 microseconds now has gone to several seconds. So it's a big step from just a few years ago, right? Where now you're able to store wave function in the core of an atom, come back and extract it at the single spin level. So I think that's pretty neat. And the question is, what do you do with this? And now a lot of people are thinking that this could be an important block for building things like quantum repeaters. Okay. I'm sort of realizing now with the time, I'm not sure I want to talk about the next stuff. Because I'd like to talk about the last stuff. Would anybody mind so much if I skip some things? I was going to talk about orbital control of spins, which is some more recent work, but maybe I'll skip that. Should I skip that? I'm going to skip it, because I can see the rousing enthusiasm for it. But I'm going to skip it just by showing you the data instead of all this stuff. I'm just going to skip all this lab stuff. But I want to maybe just mention the idea before I go into the last part of what I want to discuss before we wrap it up tonight. And the idea was that there's been a lot of experience in semiconductor physics of controlling the orbit of particles. And the idea here was because there's a spin-orbit coupling, just like we talked about in the first part this evening, the spin and the orbit are always connected. If you can control the orbital state of a particle, and there's a spin-orbit connection, by controlling the orbit, you also control the spin. And there are a lot of methods that have been known to do orbital control. And so what we've done in some experiments at the end of just this last year are to show that by taking advantage of the fact that there's strain in these materials, where the strain actually lifts the degeneracy also in orbital states, you can control with pulses of light where you put the orbit of the particle, let the spin-orbit interaction do the work for you, and then at a time later send in another pulse of light, not to do any type of spectroscopy, but to drive the system back into the ground state. So the idea is to use an optical gate. Let a pulse of light excite an orbital level, and then sometime later send in a second pulse of light to drop it back down. And that's what you do. You just gate the particle up and down, and use the spin-orbit effect to control the spin. And I won't go into the experimental issues. Any of you that are really interested can look at this article in Science that came out. But what I would like to show you is what comes out of an experiment like this. And then we'll move to the last part of the talk. Because I think at the end, what this technique has generated is not just that you can control and then monitor the excited state Hamiltonian of a particle, but it can be used in other material systems to really understand the physics of a single electron in different material systems. So if you use this technique to gate a particle up and down, you can look at the orbital dynamics. You can also look at the spin dynamics in the same experiment. And I want to just show you quickly what happens. What's neat about the orbital dynamics is use these techniques, you can go from the femtosecond to the nanosecond time frames pretty easily. So you can cover 6 orders of magnitude of time. And you can look at all the different coherences in this particle and in this system. So if you have a ground state, and this is an orbital energy diagram, and you have the excited state degeneracy split by strain into different orbital modes, you can do this experiment looking over very short periods of time. You send in a pulse of light, and then you look a few femtoseconds later. And what you find is you see a nice periodic structure, which turns out to be a frequency of 470 terahertz, incredibly high frequency, a very high frequency coherence. And in fact, that 470 terahertz is exactly the energy splitting between the ground and excited state for this particular orbit. If you now zoom out in time, we're going to look at this, the amplitude of this oscillation. We're going to zoom out in time. Those orange lines, these peaks themselves are oscillating. Okay, so what I'm showing you there is just a little slice here. If we zoom out, and now we're at the 500 picosecond, not femtosecond region, you see another frequency of 11 gigahertz. 11 gigahertz is the splitting of the 2 excited states, another coherence in the system that the system's experiencing. We zoom out again in time and go into the nanosecond region, you can see the whole thing is decaying. The orbital coherence itself is going away. So one of the things these experiments made us realize is, first of all, it's clear that the spin-orbit interactions, even in single particles, do matter. The second thing is, what's limiting orbital coherence? What limits this time scale? And has that affect all of the spin coherence times people are seeing in these systems? So I like this example because it shows a new experimental technique. It's giving us a window into some other physics in these systems. And it's actually raised some pretty interesting questions. This is one that my own group is trying to understand now pretty deeply. What limits orbital coherence in a solid? So I'm not really doing justice to this work because we don't have lots of time, but I want at least you to be aware that you can use techniques like this to measure orbital coherence. Now, since the spin and the orbit are connected, we can take in the same electron, in the same sample, instead of looking at the orbit, we can look at the spin coherence. So it's sort of a neat thing. We don't do it exactly the same time, but it's the same particle. And I'm going to skip the details of how you do this and all the energy diagrams. But basically, let's just look at the data. Sorry about all this. I hate when people do this. I didn't want to do it, but okay, just another lie. So we can now look at the spin of that same particle by preparing the spin in the x direction and measuring either the x or y or z frame. And that's what these blue, orange, and green curves are. We can do spin projection of the Bloch sphere of this particle and actually look at the coherence. And we can control the rotation by controlling how long that particle is in the excited state. So I mentioned this technique. You excite the particle from the ground to the excited state, and then sometime later you send in another pulse of light, the same pulse, you drive it back down. So based on how long it stays in this excited state, the spin will persist, so the spin-orbit interaction. And then you drive it down, it stops. and then you can do quantum state tomography and look at exactly what that spin state was. So it's pretty wild. The orbit is controlling the spin precession by using light to control the orbital excitation. And you can measure the coherence along the 3 different frames of the Bloch sphere. And if we think about that nuclear experiment where the electron and nuclear spin levels can actually be aligned, we kind of have the anti-crossing. If we do this experiment in that region to make things slightly more complicated, you can change the basis for your spin rotation because you're mixing the states. So in a way, it's like taking your XYZ frame and moving it. And if you do this through a very nice mathematical simulation, you can show you can pick any arbitrary axis and do this, which means you can control the spin in any frame you'd like. So it's pretty wild. These were examples in this paper you could look at just to show you could, for example, compare the spin initially in the Z direction, measure in X, Y, and Z. You can rotate the angles. The point is you have enormous control of this quantum state through just a 2-pulse optical experiment from one particle. And what that means is that you can manipulate how fast this spin will move. You can tune its frequency. You can change its angle on the Bloch sphere, all through optical techniques. So I thought this was a nice thing to try and end up with in terms of state control because it's a big step from years ago taking ensembles of spins and using Stark effects to move them around at low temperatures and high fields to ending up with a single particle, right? This actually was a lower temperature measurement, and having very precise quantum state control in an ordinary material. I think this is going to help us learn a lot about the physics of signal spins in different material systems. And that's what I wanted to end up with in the remaining time we have this evening. A lot of the work in our field at single spins, with single spins looking at defects, is based on diamond. And a lot of people have been doing a lot of work. They've been planting things, building photonic cavities. This is work that HP Labs was doing to make photonic structures, I think, quite far ahead of many others. They developed some beautiful fabrication techniques with thin diamond membranes. It was a real tour de force to make that work. Electrical gating, but at the end of the day, you have small pieces of diamond that you're using. And that led us a number of years ago, and this is where I want to end up in the next 10 minutes, thinking about why is all of this working in diamond? Much like years ago, we wondered why was all this working in these materials like gallium arsenide and zinc selenide? What was unusual about that? Why does all of this work in diamond? And that's where we got together with Chris van der Waals' group in Santa Barbara to do some initially first principles theoretical calculations on diamond to figure out what were the important questions to ask. Why did this actually work? And then could we use those parameters in the type of material screening to go through a lot of other materials and see what else might work. So it's not that different from techniques used in biology and chemistry in functional synthesis to see what we could use in materials theory for diamond. And about a year and a half later of running this code, they had 7 or 8 initial materials that came out of it. And just to give you a sense, this is a column of band gaps, spin orbit splittings, whether they're stable spinless nuclear isotopes, and materials. What was striking to me about this is these are all very common materials. So diamond is here. And these density functional theory calculations were remarkable because they had really quantitative predictions. They weren't just saying, oh yeah, you'll see something, right? They said, this is the frequency, this is the type of defect, this is where you should look, this is the temperature dependence you might expect, and they'll be stable. They're really quite remarkable. So if I wasn't a believer in density functional theory then, I certainly am now. So we started, and I'm going to just show you in the remaining time silicon carbide, what's happened in the last actually year or so about this, because it's a great example to me of how theory and experiment have come together in this field. Okay, and just to give you a sense, these are the types of numbers that comes out of this theory, right? The spin of the ground state, whether they're spin-conserving optical transitions, the energy, the structural stability, the probability of actually forming one, the charge state is given Fermi energy. I mean, really important quantitative numbers for a material system.
I don't know that much about the DFT calculations, but I thought that they were not that good at impurities.
I'm sorry?
Are not good at calculating impurities, right?
No.
So,
Well, they're missing atoms, so in that sense they're impurities. They're not adding dopants, but they're like pulling out atoms. And saying if you pull out an atom from a lattice, how does it affect the electronic structure? Which says, you can imagine it's a complicated calculation. And the bottom line is it worked very well. And what motivated us for pictures like this. So this is typically what people work with in diamond, right? This is typically what people work with in silicon carbide, right? And for those of you who have done some semiconductor work, you can appreciate if you're doing things with silicon, this would be considered a very small silicon wafer. But this is state of the art. And the hardest part of getting silicon carbide samples for a lot of us is actually buying one wafer. It's very hard to buy one. So when you call up a company and you want some silicon carbide, they usually say one what? And when you say one wafer, they usually don't believe you. They say like 1/100, one box, one carousel. So it's hard to buy one, actually, which is a good sign for those of us in the field. So, but we were very nice. Cree was very generous. They just gave us a couple of wafers, very persistent students, as samples. And in the US, there's actually a large initiative now because silicon carbide is a very, very popular material for high power electronics. It's used a lot today. And if you've used a hot plate in your lab, you've been using silicon carbide electronics. It's all over the place, particularly in avionics. So lots of aircraft engines run with silicon carbide electronics because they work at very high temperatures. And these are just examples of why it's such a popular material right now. You can go online and buy power MOSFETs for silicon carbide. They're very popular for MEMS technology. Lots of airbag deployment systems are running with silicon carbide, just for mechanical resonators, right, for high frequency. Lots of beautiful work now in graphene is being done by just flash sheeting silicon carbide to form a layer of graphene. And that's actually quite nice because you get graphene gates on silicon carbide. So it's a very, very nice material system, and because it's been around for a while. I mean, if you dig into literature in the 90s, people were making pretty impressive integrated circuits with silicon carbide, like this non-volatile RAM with control, even at that time, were being done for avionic applications by electrical engineers. So the reason I'm saying this is that there's a lot of literature out there for how you build and fabricate with these types of systems. So there's a lot of advantages in using it. And so recently, there's been work, for example, in our own group of making photonic structures with silicon carbide. There's been some very beautiful work at Case West and other places to make torsional oscillators with silicon carbide, with freestanding membranes. Again, because they're nice fab recipes for it. And at least very happy students, because I'm sure some of you can appreciate that if you've dropped your diamond sample in the clean room and you can't find it. I'm guessing your advisor is not as enthusiastic as you might be about that, where if you drop a silicon carbide wafer on the floor, it's no big deal. It actually is no big deal. So Greg was very happy. So I'm going to quickly show you why this was so cool for us. So we got Cree to send us some samples. We just took the samples, we took them out of the box, did the experiments. And sure enough, went down to 20 Kelvin. These were ensemble measurements, about 200 spins. Beautiful coherence. We looked at did Hahn-Echo measurements at the time to look at these samples. These were dye vacancies, so there was both a missing silicon and a missing carbon atom. Okay, and when we looked at these, they were right at the wavelengths that the DFT theory had predicted, which is actually just at the edge of the telecom frequency. So it's actually in the near infrared, which is very nice for a lot of other reasons. And there are different types of defects because they're different lattice orientations. And one of the particular orientations worked nicely at room temperature. So they were right, these silicon carbide calculations. We have another system now, room temperature. You'll see in a little bit when you clean up the material, they look like diamond. If I didn't tell you what the material was and I took away the wavelength, you would be hard pressed to know what it was, particularly the single spin level. There were some different structural degeneracies that led to these beatings in some of the data. They were just spins at different angles that are at slightly different frequencies beating. But the message here is that the lifetimes of the single spins are about a millisecond, same ballpark as diamond, but in another system. So that gives us a lot of promise for how this field might go. Silicon carbide also comes in different polytypes. Do you know what a polytype is? Sounds like a social disease. Oh my God, I have a polytype. But so polytype just means that you can have the same crystal structure in the XY plane, but the Z axis can be different in different crystals, the Z separation. Okay, so it's a crystal that just will grow in different types of forms, and there are over 250. They're actually discovered in meteorites. So silicon carbide was first discovered. It can be cubic or hexagonal. For any of you that do materials, that's a very rich property. It means you can grow different materials on them. or them on different materials because of the different crystal symmetries. And because of these different z-axis spacings, it means the band gaps are different. So it's quite a cool material. It means, for example, you can grow quantum wells with the same material. You don't need to mix materials. You can have silicon carbide on silicon carbide on silicon carbide, but if you grow it with a slight different structure, you'll form quantum wells. So it's actually, it's quite interesting. And a number of these structures can be grown on silicon. So remember I was telling you about one of the challenges of diamond is finding a substrate to grow diamond. One of the nice things about silicon carbide is you can grow it on silicon. The nice thing about growing on silicon, and those of you who worked in the clean room know, means you can process it very nicely. So very quickly, what happens when you do this? So you can do some interesting experiments. You can actually, because these different spins and different orientations are at different energies in the lattice, you can manipulate one spin type and look at the other. And if they're dipole coupled, you can look at dipole coupling. This experiment shows, for example, in the black curve, you're driving one spin species at one frequency, and the blue is the response of the adjacent one. So an experiment that's been quite nice to do theoretically for some time to say take Ising or Heisenberg systems and let them be dipole coupled and manipulate them. Now you at least have a toy system in the lab, you can do that experiment. You can actually have identical spin systems which can now be distinguished from one another because they're different energies, different wavelengths. You can make particles much like diamond. They work equally poorly, but you can go through the same implantation process. But what's interesting now, just in the last year, is that you can go to the level of single spins, just like I've been referring to in diamond. And since the spins have different lattice orientations and different energy, you can actually distinguish in the lattice which single spin you're looking at based on its wavelength, which is pretty cool. So you can see here there are defects in different orientations. Each one, because the electronic structure around the defect is slightly different, the wavelength will be slightly different. So if you look at the light that comes out of the system, and you look at different defects, this is the luminescence, you'll have different curves at different energies. You can map each one of them through the theoretical modeling to the specific orientation of the spin and drive the Rabi oscillation of the specific defect you want. So it's actually, I think it's quite remarkable. You can drive these Rabi oscillations of a spin in a different angle in the lattice, one spin at a time, based on its energy. So there are a lot of fun things you can do with this. And to me, one of the more amusing things about this is that if you look at the lifetime of these spins, the lifetime is pretty long. And it's quite interesting that it can be a millisecond or so in a system that's filled with nuclear spins. So at first blush, you would think that you'd have all of these spins that would dephase the electron. You have all these nuclei, right, over huge ranges, creating these random fields. And yet, you still have pretty nice coherence times. So there's some nice theory models about this that have come out in the last 6 months. But it's giving us some hope that maybe materials that we tossed away thinking they wouldn't work so well may need to be looked at again because, in fact, they're working pretty nicely. So where's all this going? You could use electric fields in piezoelectric materials like this to manipulate spin. Again, because of the sake of time, I don't want to go into this now, but another property of some of these systems that are on that table that I showed you earlier is they're piezoelectric, which means very small electric fields should be able to be used to manipulate the spin. And last year, some nice experiments came out showing that using just electric fields, you can do electrically driven spin resonance and electrically drive Rabi oscillations in silicon carbide. So I've been talking about the fact that you'd like to use electrical gates and techniques to drive spins. So if you choose a host system that's piezoelectric, you can do that, which I think is, is interesting. And at the end, people are now beginning to think, what can you do besides computation with quantum states? And lots of discussions being about sensing. I think most people in the room probably have heard about magnetic field sensing. With spins, it makes sense. If you have a quantum state, you can move it around a magnetic object and sense it. This is some quite nice work that was going on in Australia by having nanoparticles in cells and seeing if you can measure the internal fields of the cell, which they did very nicely. A lot of this hinges on being able to make small quantum sensors by carving these materials like diamond into very small particles, and at the end of the day, releasing them so you can use them. If this were silicon, this wouldn't be such a big deal. Diamond, it's a bit harder to create a large, just like sort of an array of diamond soldiers here, ready to go, of different sizes. But if you look carefully at this image, they're actually tethered with a bit of polymer, PMMA here, that then you can ultrasonicate and release them from the surface. catch them with filter paper, put them in solution, and then inject them into a microfluidic circuit. So now you have some free floating little buoys, right, that can go in a fluid with electron spin in them as sensors. And so there's a sort of blow above them. And one of the nice things you can do with the quantum state that we haven't talked about is you can change the way that you apply pulses to these systems and change the way you read them so that they're very sensitive to temperature. And if you look at the phase of the beating particle, in this data you can see if you change a tenth of a degree, you can see at the particular time there's a pretty big change in the phase. So if you design these carefully with the right pulse sequences, you can actually use these as very precise thermometers. And that's quite interesting for a lot of problems in biology, where a lot of biological processes are believed to be thermally driven, but there's been no way to measure them because you need to do a measurement at a specific site at maybe the submicron scale, which is actually pretty hard to do if you want a part in 10 to the third or part in 10 to the fourth temperature sensitivity. There just haven't been probes to do it. So in our own group, we're working now with some people in the biochemistry program in Chicago using these probes to measure thermal differences in cell walls, to try and understand some of these processes, meaning they're doing it. And one of the fun things about making little probes like this in microfluidic systems is you can scale fluid measurements much like you can scale electronics. Not to the nanometer scale, but to the submicron scale. Make small channels where you can inject your experiment, use optical traps to hold these little quantum probes where you like, flow different fluids around them, and actually sense what's going on with this change in the beating of the quantum state. And this is just an example of the sort of thing you can make with PMS, is plastic stamping. These take a student about a day and a half to make. They're disposable, they're all made of plastic. They sit inside here. This is a little special because there's some ESR coils here to apply microwaves to these spins. But these are fluids that are injected into the chip. This was not funded at the time, so we just used syringes, just did it all by hand. The students have no trouble coming up with syringes. Okay, and the amount of fluid you use are very small, if you're about 100 nanoliters. So the idea is you can do this very small amounts of fluid, very small numbers of particles, and actually you can recycle the diamond particles when you're done with them here. Just to give you an example of what you can see, there's a little particle. This one actually had 2 spins in it. And you can do ESR on these spins in solution in these chips, and they work pretty well. And what's surprising is that the coherence times drop maybe a factor of 10 to a factor of 2, but they work pretty well, even with all the surface around them, even though they're small probes. So I think I want to stop here. I think a number of you have seen that groups around the world, both in Stuttgart and IBM, have been trying to do NMR, also trying to push the level of sensitivity to the nuclear level. It's a very big challenge. You can see nuclear signals, but the real goal of these experiments, a lot of you probably know, is to do structural imaging. And for structural imaging, you need to get X, Y, and Z directions, say of a protein. And you probably also know as you move a spin away from the surface, the signal drops quite a bit. Particularly the nuclear spin signal drops very fast. It's a very big challenge to be able to do that. So while in our own group, with our own work with the Dominant Group, it's been possible to look at nuclear spins, and very recently, just a couple of weeks ago, we got this very globby picture of a molecule. It's a nuclear image. It's not a particularly inspiring nuclear image. As our program manager said, it looks like a blob, which we felt really great about after 2 years of work. But it's sort of a state of where we are right now. It's not great, it's 12 nanometer resolution, but it's a room temperature nuclear image. So a few years ago, a lot of us felt this would be very, very, very difficult, if not impossible to do. And at least it's a step. But again, right now, we have a lot of challenges trying to think about how we'll get an actual structural image out of something like this, but it's exciting to know at least there's a pathway at room temperature to start doing NMR imaging with quantum states. So I think I want to stop here, but I do want to mention after all of this that, of course, as some of us were discussing in the break, that at the end of the day, all of this work is being done by the students, even though I get to come here and spend an evening with you. And it's a pretty great group of graduate students, and the 4 that I've outlined here are the ones that did a lot of the work I just talked about. Chris Anderson, Paulo Andrich, Chris Yale, and Joe Hermans. And Hope is an undergraduate who worked on quite a bit of the sensing work with us. Is actually just won a Marshall Scholarship, so she's going to be in both Edinburgh for a year and then at Cambridge, continuing on with some of these efforts. So that's it. That's sort of where I wanted to end things. It's been a bit of a long evening, I suspect, but I hope it's told an interesting story, how these fields are moving pretty fast, and honestly with a lot of surprises. And I think actually for those of you who are working in this area, it's an incredibly neat time to be in this field. Because I'm pretty confident that there's a lot of surprises in the past, a lot of unexpected things now. I'm sure that's going to continue on in the future. But the fact is, in the last few years, the fact you can measure and control a single quantum state in different materials, and the list is growing. Groups in Japan have now gotten this working in zinc oxide, which was also on the list. Another quantum system is working nicely. I'm sure as people move down this diagram, there'll be even more. You can engineer the spins through a lot of new materials growth techniques. Some pretty neat new devices have been put forward. And it's not clear at the end of the day where this is all going to end up. A lot of this was driven by quantum information processing, but I think if you pulled a lot of scientists in the room, you would probably get the majority saying if you could actually do NMR at the single protein level and do actual structural imaging with a quantum state, you would revolutionize biochemistry. And which I...
And medicine?
Yes, absolutely. I mean, how many proteins can actually be crystallized now and studied with a synchrotron? Very few. If you suddenly could remove that obstruction and actually had some tool, some experimental technique where structure-function relationships could be done on individual proteins, it would change everything. I mean, it would be an enormous accomplishment in science. And at the end of the day, the ability to control quantum states for that application could supersede anything we've been thinking about right now. So to me, part of the fun thing about this field is it's not clear exactly where it's going. It's like going down some highway at 100 miles an hour on low beams. You're trying to stay on the road. You can't really see where you're going, but you're going somewhere. And I think that's where we are right now. So it's an exciting time, and we'll stay on the road. So anyway, thank you very much.